Greeting everyone. In previous class, we have discussed the factors affecting resistance. In that, the prime example was temperature, and we had the formula of resistance. This, right? And in that we know that mass of electron is going to be constant and the charge of electron is also constant. So the only thing you can change is area, length, and tau average and free electron density. And here we had that statement that dimensions of the conductor is going to be constant. So in that case, the only variables we had to discuss was free electron density and your tau average. And we had discussed about what? Conductors, right? Remember? And see, all the topics are in a sequence in which you can get the idea. And here before even we started this, I have already explained you about the concept of free electron, and there I explained what is your energy band and all. So for metal, I have already told you that energy band, this is your valence band and this is your conduction band. The gap between energy band is very, very small. Sometimes it overlaps also, but the gap is fairly small. That's why electrons can easily jump from your conduction band to what? Sorry, valence band to what? Conduction band. And that is the reason that in conductor there are many free electrons in the conduction band. For example, I told you that for metals, for copper, the free electron density is around 8 point something into 10 raised to the power 28 meter per meter cube. That many electrons you have in a 1 meter cube of sample of copper. So they have already very high number of free electron density, and you can see the resistance has inverse relation with N, and also it has inverse relation with tau average. So furthermore, what we have discussed that on increasing temperature, your N increases but tau decreases, right? You should be aware of this because we have just discussed in previous class. And considering this, one factor is trying to increase the resistance and one factor is trying to decrease the resistance. But here we have concluded one more thing, that because metal has such high value of free electron density, what will happen? The change in N will be not so significant that we are going to consider it as a factor. Means it is a factor, but in compared to tau average, it will be insignificant. So overall, this factor becomes what? Dominant in the case of conductor. That's why the only factor which affects resistance on increasing temperature is your tau. And you can see, if you have inverse relation with tau, we have already discussed all this inverse relation, and on increasing temperature it decreases. That means resistance also going to increase, right? We have discussed that on increasing temperature resistance increases for a conductor, and there are only two factors which are going to affect it, and one factor we have said that it is going to be not that significant because they have already such high value of free electron density. That is the reason that what you are saying is that tau average becomes your dominant factor. So this is what we have discussed about conductor. Later on we have to discuss about, again, all the theories you are seeing that one factor is dominating, another factor is not dominating, and all in all this has been thought after doing the experiment. It is not like that you got the theory first then the experiment. All these are based on electron gas model. All these are based on electron gas model, that kernels collision and all these are based on electron gas model. So on that basic we are discussing. First we did the experiment, then we are giving the reasons. It is not like that in physics every time it happens like this only, but many time it happens. Now we are going to discuss about something else, that is your semiconductor. See, semiconductor will be your one of the last installment of the 12th class physics, but here I will give you a little bit of idea of semiconductor. There are two types of semiconductor. You have intrinsic and you have another one. Okay, so we are going to generalize that, and we are not going to differentiate and all, but we will have the basic and general idea. For semiconductor, what happens? I think in resistance and resistivity also I have explained. Semiconductor, what happens, that the gap between them is larger compared to conductors, means metal, but it is less compared to insulator. So they have moderate energy gap between your valence band and conduction band. What means, what does it convey to you? That if you want to have electron in your conduction band, that you are going to need a photon with much higher energy or much lower wavelength, so it can knock out the electron and send it to conduction band. So compared to metal, they have very small value of free electron density in their conduction band. So remember this, the free electron density of semiconductor is much lower compared to the free electron density of metal. Okay, that part you understood? That is the reason, I have already told you, that is the reason they are not so good conductor. That's why they are not so good conductors, right? And if you know the pures, if you know or if you don't know, we will discuss on the end of semiconductor, in semiconductor, that pure semiconductor is not, it is not even that much conductive that we can use in a circuit. We have to put some impurities. So just alone semiconductor is not one of the things you can use in any circuit to make it conductive enough. For example, you have in semiconductor, you can have germanium, you can have silicon and all. These are your basic types of semiconductor. So you understood that part. The N is very, very small compared to metal. Now same thing, the formula of resistance is not going to be changed. The formula of resistance will remain same. Mass of electron times L by N E square A tau average. Okay, so if you have a semiconductor connected to a source, again we are assuming the area, means cross-sectional area, we are taking as constant, and length also we are taking as constant. The only factor here again changes your what? Free electron density and tau average. So what happens here for semiconductor? Again, on increasing temperature, again your N increases, but on increasing temperature your tau decreasing. Same theory applied, nothing fancy here. So again, you can see one factor is trying to increase the resistance and one factor is trying to decrease the resistance. Again, we have to discuss which will be dominant here and which will be not dominating that much. So the basic idea here is we did some experiment and we found out that if you increase the temperature of the semiconductor, it becomes more conductive. And it is obvious that you can see here also, if you increase the temperature, what you will have more photons of higher of higher energy, which can knock out the electron from valence band and send electron in conduction band. And if you have more electron in conduction band, then what will happen? You will have more electron which can move freely in the circuit and which can increase the conductivity. So simply they have very low amount of free electron density, and if somehow we are able to increase the free electron density, it will become more conductive. That is the reason that in this case your N is more dominating compared to tau average. Again, it all becomes conclusive only after doing the experiment. It is not like that we have given the theory first and then we found out the result while doing the experiment. It is opposite of that. And you can also have this, you can also do this experiment also to verify what I'm saying. Just buy one LED, and if you know the LED has polarity, it has cathode and anode, and if you put it in like reverse polarity, there will be no conductivity. But if you increase the potential by some amount, and then what will happen, that it will become suddenly conductive. I know if you have the idea, you might be thinking about breakdown voltage and all, but the theory is still remains same whether you connect with polarity and without polarity. So you can do the only loss you will have is just one LED to verify what I'm saying. So what I'm saying here, that experimentally we found on increasing temperature, resistance decreased or conductance increased, whatever you want to say. That means your N becomes dominating here. Got it? Your N becomes dominating factor. What is the reason? Because already they have very small amount of free electron density. If somehow we can increase the number of free electron density, then it will become more conductive. So here tau average will also have some effect, but the effect will signified by what? N. So you can lastly conclude here. I'll write here. Lastly conclude here, although I have already written, that on increasing temperature, resistance here decreases for semiconductors. Got it? Now there are other materials like insulator and all. What do you have in an insulator? See, insulator, although we don't need to discuss much about insulator, that is not in this syllabus, but I'll give you the general idea that insulator has very large gap in their valence and conduction band. So they already have very small amount of free electron density. Even if you heat them, there will be no significant difference in their free electron density. The reason simply lies here is the method by which you will heat, before they can send their electron from valence to conduction, they will start burning, and thus they will not be that conductive. But again, one more line I will say, anything you have, whether it is wood, iron or anything, even though if it is a bad conductor, if we have large enough potential difference, then it can becomes conductive. You might think I'm contradicting my statement, but that is the correct statement. In further class I will explain the more analysis of what I have said, but it is true. You have seen lightning, right? Lightning occurred in between what? The space, the air, right? Air is not conductive. Air is very good insulator. It also is good to it is also bad conductor for heat as well as electricity. But still we have seen the phenomena of lightning. That happens because the potential difference between cloud and the ground becomes so high that it makes the chain of air molecules conductive for that path, and air becomes conductive for that particular instant. So anything can become conductive if we have large enough potential difference. But because we have most of the time we don't deal with that much high voltage, so we have only some certain range of voltage. So in that voltage we have to figure out which can easily conduct electricity and which cannot. So that's how we have defined what is good conductor, bad conductor and all. But as you will go in engineering and all, electrical engineering, you will also study there is something called skin effect, and you will realize that even the conductor which you think is conductive, it can be also bad conductor if there is a AC source and the frequency is not suited for the dimension of that conductor. So there are many things you have yet to study, but all this will come when you study higher physics. For higher physics you have to study higher mathematics. So I gave you the idea of insulator and conductor we have discussed, semiconductor we have discussed. Now we will discuss alloy. See what is alloy here? What we are trying to have in alloy here, that these are the materials which does not change their resistance on increasing or decreasing the temperature. These are such type of material. And why we need to have these type of material? See, we have many devices like ohm meter and voltmeter and all. These things needed to be calibrated to measure the readings, in any experiment. For that they have to be calibrated. For that you need some device for which the resistance does not change that much while the temperature changes or not. Again, so the basic idea of alloy is that the resistance will remain nearly same even if you increase or decrease the temperature. Although it cannot be exactly same, there will be some change, but the change can be ignored. So this type of change we are talking about. So alloys are these are designed to have nearly constant resistance even on change in temperature. But you have to remember, I have said this, but you have to remember two statements, that the resistance does change, but the change is very small. Another thing you have to remember is the change in temperature which we are talking about, it should not be too high. It should be like very moderate, like change in temperature by 20 degree, 30 degree, 50 degrees, somewhat like that. You cannot have like change in temperature around 400 degrees Celsius, 300 degrees Celsius, something like that. So if there is a large change in temperature, the resistance will change and the change will be significant. So if you want to have nearly constant resistance, the change in temperature should not be that high. So first thing you need to remember, resistance does change, but with very small variation. Secondly, what you have to remember, that for that change in temperature should be moderate, like 20 to 50 degree Celsius, right? If you have higher change in temperature, then the resistance will change and the change will be significant, right? Okay, so alloy, as you can see, it is not made up of one type of material. It is always it is mixture of some different element like manganese, or you can have constant 10. These are the examples of alloys. For that, what you have, their resistance will remain same. From this you can get the idea what we are approaching. So if you have resistance form, you can resistance formula is nearly constant. That means n and tau both should cancel out each other's effect. So we can see on increasing temperature, we know n increases and tau average decreases. That is true. And if you want to have nearly constant resistance, what you need to have? If you want to have constant resistance, n average, free electron density and tau average will do what? They will cancel out each other's effect. Right. The cancellation not exactly 100%. It is still here. What will happen? The resistance is going to be slightly increased. That means tau average is, if you still want to know, tau average will be slightly more dominating, but the domination will be very, very small, because the changes we are talking about is very small. And why is that? Because they are designed in such a way that they are meant to cancel out their effect, so resistance will remain nearly same. And again, I have said these sort of things are used in what in devices to measure nearly accurate values. Again, you cannot measure anything with 100% accuracy. There will be slight error always. So these kind of alloys are used to make wires like manganese wire, constantan wires, nichrome wire. These wires are used in, like, if you have seen meter bridge in your school, potentiometer in your school, there they use these sort of wire to measure resistance or internal resistance of battery or battery's EMF with higher accuracy. And also, if you ever Google the ohm meter, which can measure resistance with far more accuracy, like up to 9 decimal places, it comes very costly. Also, it uses an alloy which has very precise value of resistance, which hardly change with increase in temperature. Got it? So they are designed in such a way that they can be used in this sort of calibration. So we understood everything. Now we are talking about mathematical approach here. Mathematical approach means we want to figure out how we can calculate the change in resistance with the help of change in temperature, or vice versa. So for that we need to have an equation. We have to have some mathematical relation that only can be used to determine the change with accuracy. So for that I'll show you two observations. Pay attention to that observations. Okay, so first experiment was simple. You had two resistors, R0. These two are identical. Identical in anything, identical in dimension, identical in resistivity, everything. Their resistance is also same because they are identical. Okay, and both were set at temperature, you can say T1 or T0 for simplicity here, T0. Got it? So what we did, we increased the temperature. Here we increase the temperature by 25 degrees Celsius, and here we increase temperature by, let's say, 80 degrees Celsius. Arbitrary number I am picking. The only thing matter here is I have taken this change higher than this one. So you have identical resistance, and we did we did increase resistance by some amount. So here what you will found that the material with smaller change in temperature will also have increased resistance. This will also have increased resistance, but the difference will be here. Let's say this resistance becomes R1, this resistance becomes R2. We can see here, this is your what? Change in temperature. Let's call change in temperature T1 and change in temperature T2. Right? They both will reach to temperature. This will be T0 plus 25 and this will be T0 plus 80 degrees Celsius. So we can see here that change in temperature 2 is more than change in temperature of 1. And it is very obvious that you can see the resistance of material which has higher change in resistance will be more. That means R2 will be higher than the R1. So from there we can say that change in resistance is directly proportional to change in temperature. If change in temperature will be more, then the change in resistance will be more. Means if you drop the temperature, it can decrease also, but it is directly proportional to the change in temperature. Again, this is experimentally, this is the observation we have done. Observation 1. Second observation was we had a material, some material or conductor, this and this. Now you can think it like this, that they both have same resistivity, or you can again think it in different way also. There is no point. Just what I'm trying to say is, imagine this is R1 and this is R2 and this is temperature T0. Both are set at same temperature. The only difference I'm talking about, R2 is more than R1, right? So if we have two materials, pick it from same set, like they can, it is not necessary they should be same material, but if it is conductor, then you take it, this also be conductor. You can think this is copper and this is silver. Again, one more thing you should know, silver has the least resistivity. Okay, even it has lower resistivity compared to gold. So if you have two material, this one and resistance of R2 is more, but they are at same temperature. So if you increase the temperature of both the conductor by same amount, means let's say 50 degrees Celsius, here also 50 degrees Celsius, right? Means change in temperature is same for both of them. So what you should think, or what is the general perception, that if change in resistance is, change in temperature is same, what we will get is the change in resistance should be according to that only. Means change in resistance should be equal. Again, it will have higher resistance, it will have lower resistance, that is fine, it is obvious, but change in resistance should be same. For reference, what I am implying to say, that what I'm trying to say here, that this and this, let's say initial value was let's say 50, here 30, and let's say because change in temperature is same, so let's say resistance increase by 20 and 20, so this should be 50 and that should be 70. But what we figure out that even the change in resistance, I'm not talking about the final resistance, I'm talking about the change in resistance. See, you should know here final resistance, let's call it R1 dash, will be your what? R1 plus delta R1. Here your final resistance will be what? R2 plus delta R2 dash, right? The change in resistance should be what? Same. Should be same. But what we found that the change in resistance of 2 is more than change in resistance of 1. You might think like, sir, okay, it is fine, it is possible because you have taken this as different material, this as different material. Okay, you would have been correct, but even if you take this as copper and this as copper, just their different values of resistance, the conclusion will remain same. The one material with higher resistance will have higher change in resistance compared to the lower one, irrespective of their resistivity. And same thing is true for resistivity also, right? So this was found experimentally, right? So that concluded what? That change in resistance is also proportional to the initial value of resistance. And if you remember, you have seen this in somewhere, and where is that? That is class 11 and thermal expansion. If you remember thermal expansion, you know change in dimension is directly proportional to the change in temperature, but it is also directly proportional to the initial value of dimension. Here we are getting the same similar equation. The change in resistance is proportional to the change in temperature, but it is also proportional to the change, it is also proportional to the internal resistance. And if we combine all the things which we found out, that change in resistance is proportional to the change in temperature, as well as change in resistance is proportional to the change in initial resistance, the equation or the final term will get what? Change in resistance is directly proportional to the R naught delta T. And if you remove the proportionality, what will get? Delta R, some constant, and that constant also is alpha, R naught delta T. And that R naught is called as thermal coefficient of resistance or resistivity. Thermal coefficient of resistance or resistivity, right? You can more generalize this equation. You can write it like this: R, this means what? R final minus R initial, right? And this will be, you can also write what? R final minus R initial alpha R naught delta T, right? It is your choice. I'm just writing because in many books they write it like this. If you send it there, you will get what? R naught plus alpha R naught delta T, and again you can generalize and you will get what? R final, take R naught common, you will get what? 1 plus alpha delta T. Correct? This will be your equation. And again, if you want to define alpha, alpha will be your what? You can see from the equation, alpha will be your what? Delta R by R naught delta T. And from this you can see the unit of alpha will be just what? See, change in resistance will all again will be considered into what? Ohms, and R naught will be also ohms. So unit will be just per Kelvin or per degree Celsius. So what is the definition of alpha? Alpha, you can simply define alpha is how much the resistance will change for a unit resistance conductor when the change in temperature increased by 1 degree Celsius or 1 Kelvin. To define anything in physics or chemistry, what you can do, you can make denominator as 1, and from that you can define what is your alpha. So simply alpha, again I will tell you what you can write alpha. Alpha is just what, how much there will be a change in resistance when 1 unit resistance temperature increases by 1 degree Celsius or 1 Kelvin. That's how you can define alpha. Again, what it generally alpha in your books, from this equation you can get, or from even sometime in books they will write alpha is constant. But again I'll tell you, alpha is a function of time. Alpha is function of time. Alpha is function of time. Sometime in like good question you will see alpha as a function of time. Also we'll see the graph of alpha, or maybe we'll see the graph of resistance versus temperature. There we'll get more explanation of alpha. But remember this, alpha is function, sorry I was saying time, sorry I'm saying alpha is function of temperature. Okay, alpha is function of temperature, means as temperature changes, alpha also changes. But for small values of temperature or small change of temperature, many times we can take alpha is constant. So in this class we have discussed about alpha and other two topics, and next class we will discuss what? We will discuss about some numericals and some graphs and superconductor that we will discuss.